Recording. Okay, welcome back to chapter 9. We're going to continue on with NMR. And to help solidify those 4 things we're looking for in our NMR, we're going to do this activity right here. And it's just for your edification. And there'll be an answer key online if you want to, and there'll actually blank ones online too, if you want to do it again, just to make sure you have it down. So we're going to ask ourselves 4 questions. The first one is, how many signals do we have? Okay. Then we're going to say, we're going to calculate what the intensity would be under the integral. And then we're going to predict the shift order just by what it's attached to, not looking at exact numbers. And then we're going to predict the splitting of each of these. Okay. So if we start with this first one right here, okay, you want to remember that, you have these hydrogens bonded to here, here, and here. So we'll need to make sure we know how many are there. So I'm going to call this peak A, this carbon A, this carbon B, this carbon C, and this carbon D. Okay. On carbon A, how many hydrogens do we have? 3. Okay. On carbon B, how many hydrogens do we have? 0. Okay. So are we going to get a signal for carbon B? No. Okay. Cool. Carbon C has how many? 2, and carbon D has, so we have 3, 0, 2, 3. That means we're only going to get peaks for A, C, and D. Okay. So now, not only have we figured out which carbons are going to give us a signal, we know exactly how many hydrogens are each carbon. Okay. So we've done the 2 things already. Now we want to predict the shift order in the type of hydrogen. Okay. So which one is going to be closest to 0? Upfield. Which one's going to be closest to 0? D, because it is the furthest away from any electronegative atom. So if we were going to look at this, we were going to have it, this is 0, and this is, well, let's do 5. We're going to have D is going to be furthest upfield. Okay, so that gives us A and C. Okay. A and C are going to be further upfield, but which is going to be more upfield? A, because A only has hydrogen attached to it. The carbon can donate electron density, so it's not going to be as high. So we're going to have A is going to be our highest and C is going to be our middle. Okay, so now we've predicted where we should find those peaks. And we should see 3 for this one, 2 for this one, and 3 for that one. Okay, so we can identify it by shift and or intensity just right now. Okay, so let's do the last one. So A, how many peaks is A going to have? Okay, we're going to, by spin-spin coupling. How many hydrogens are within 3 bonds of those hydrogens? 0. So our N is 0, N plus 1 is 1 peak. So we're going to get 1 peak for A. And it has 3 hydrogens in it, but those are equivalent hydrogens, so we only get 1 signal. Okay. So now let's do C. Okay. C has how many hydrogens within 3 bonds? 1, 2, 3 for the methyl group on D here. So that means we're going to have, that's our N. So we're going to have how many peaks? 4. So it's going to be a quartet. And quartets are symmetrical like that. And we're going to have 2 hydrogens in that. So let's do D now. How many hydrogens are within 3 bonds of D? 2. So that's our N. So 2 plus 1 is equal to 3. So we have 3 peaks. Okay.
On A, how come that one has because
see, there's no hydrogens on this carbon.
Well, you said 3 bonds away, right?
Right. No, because you have to count the bond from hydrogen.
Oh.
1, 2, 3. That goes to a carbon, but not the hydrogen. Their hydrogens have to be within 3 bonds. Okay. So, but good clarification though, that's important. Okay, so how do we feel about this? All right, let's do another one here. Let's do this one right here. So how many signals do we think we have? We're going to have, well, let me label the carbons A, B, C, and D. And I'm going to label that one E. Okay, because that one's there. I'm going to label that hydrogen E because we have to play with it. Okay, so how many hydrogens do we have on A? 3. How many hydrogens do we have on B? 1, because we have that 4th bond there. It's understood to be there. So we have 1 on B. How many do we have on C? 2. And how many do we have on D? 3. And we have 1 on E. Okay. So we have 1, 2, 3, 4, 5 signals. Okay. So, and we know exactly how many hydrogens are in each of those signals. Okay, so which hydrogen is going to be the furthest downfield? So it's going to be E or B. It doesn't split. You don't split it, it just has it. So when if we look from 0 to 5 again here, we're going to put E can actually be anywhere in this area here, depending on how it's hydrogen bonded. Okay, so that makes B the next highest one because it's the one bonded to the carbon directly bonded to the oxygen. It's going to be the highest. Okay, now using the rules we used for the other one, then it's going to be followed by A, C, and D. Okay, D is the furthest away. C has another carbon bonded to it, so it's not as shifted as A. But do you see why B is the highest shifted? Okay, it is within 2 bonds of an electronegative atom. It's, you know, the E, remember that because of hydrogen bonding, this can be in this entire range. So E is definitely might be the highest, but it could be anywhere in that range. But this one's only 2 bonds to the electronegative element. These hydrogens are 3 bonds to the electronegative element. These hydrogens are 3 bonds to the electronegative element. And then the D ones are 5 bonds.
So you can't really tell between A and C.
Well, you can tell the difference between A and C because C has a carbon bonded to it right here. These are only hydrogens. Hydrogens can't donate electron density, but the carbon can. So if you had to choose, the methyl group is going to be just higher than the CH2 group because the CH2 can have bonding from the carbon. Okay. All right. So we got our order together. We have our numbers and everything like that. So let's look at our splitting pattern. So first of all, E does not split, right? We don't split through oxygen. So E is just going to be, it's a little single peak, or it's probably going to be a little broader because of hydrogen bonding. Okay. So let's look at A. How many hydrogens are within 3 bonds of that? 1. So N is 1, and so that makes it 2. So it's going to give us a doublet. We see why that only has the 1 hydrogen there. Okay, let's look at B now. We have 1 hydrogen, and we have 1, 2, 3, 4, 5, and we don't count this one because we don't split through oxygen. So that means 5. So our N is 5. So that makes it 6. So we're going to have 1, 2, 3, 4, 5, 6 for B. Now, the reason we're doing this is that I want you to see where the shapes are coming from. I want you to see where the splits are coming from. I want to see where the shifts are coming from, so that when we look at the spectrum on the back of the page, we'll be able to identify which is which. Okay. So let's look at C. Okay. All right. On C, we have 1 hydrogen, 2 hydrogens, 3 hydrogens, 4 hydrogens. So N is 4. Okay. So that makes our split 5. So we're going to start in the middle and go 2, 3, 4, 5. Okay. So this is starting to make a little bit of sense now, right? You're starting to see where all these things come from. D, we have 1, 2. So that's going to be a triplet. N is 2, so we have our triplet. Okay, so now we can predict where these things should be, right? And so it makes it easier to find them. Okay. All right, let's look at this one. Okay, so we're going to have A, B, C. I'm not going to label the oxygen or the bromine because neither one has hydrogens on it. So D, we have 4 things that have hydrogens on it. How many signals do we have? 4, because this is pretty different than that, which is pretty different than that, which is different than that. So because they're all different, we're going to have 4 signals. On A, how many hydrogens do we have? 2, B, C, D, 3. Okay, so that's good. Now let's talk about shift. 0 to 5, right here. Which one's probably going to be way highest upfield? It's A or D. They're going to be pretty close. Okay, they're both electronegative, but this one at least has a carbon on it. So I'm going to say that D is going to be furthest upfield. Oops, not B. D is going to be furthest upfield, and A is going to be really close behind it.
Is the amount of electricity?
Yes. Yeah. You'll see that oxygen actually shifts it a little bit higher than bromine. So in the table that oxygen does shift it higher. Okay. And then what's going to come next? C, and that's going to be pretty close to these two because it's bonded to an oxygen as well. Yes.
Could you explain why D?
D right here is bonded directly to the oxygen and has no donation available to it. There's no carbon to donate to it. Over here, this actually is going to be just slightly below oxygen in its electronegativity. And so this is going to be just below it. And it also has a carbon to back donate some electrons. So that's going to shift it down just a little. And then that makes this one next. And by the time we get here, it's actually going to be, halfway to normal. It's going to be a little shifted down away from them. It's not quite there because it is about what, 1, 2 bonds from that one and 1, 2 bonds from that one. So it's not going to be all the way down to being just a CH2, but it's going to be away from the other side. Okay, so now let's do our splitting. Okay, so for A, we have 2 hydrogens and we have 2 next to it. So that's going to be a triplet. B has a total of 1, 2, 3, 4 hydrogens next to it. So that's 4 plus 1 is equal to 5. So we have a pentet. And then C has 2 next to it. So that's a triplet. And D has none. So a single. Okay. So again, if you go and look at the table, the bromines are just under where the oxygens are. Oxygens will go all the way up to 4.0. Those methyl groups on oxygen. All right. Questions on that one? Okay, now let's do the hard one. So we have 1, 2, 3, 4, 5, 6 signals, right? Well, no, wait. We have some tree. Wait. We have a ring. Uh-oh, we got to draw it differently now. We got to draw the ring on its side and show where those are. Hydrogen, 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 hydrogen. Okay, so now we have 1 signal for this methyl group. We have 1 signal for this hydrogen. Okay. We'll have 1 signal for these hydrogens because they're different than these hydrogens. because these are next to the hydrogen and these are next to a methyl group. And let's see, what do these see through space? They see hydrogen, hydrogen, they see hydrogen, hydrogen, and they're actually on equivalent carbons. So it turns out these, all four of these, are going to give one signal, because they're far enough away from that spatial interaction that they look identical. So we have one signal. We'll call that one A. We'll call this B. We'll call this C. We'll call this D, and we'll call this E. And so that's how you can really, miss it if you think about the actual spatial interaction where the things are. So if we look at A, how many equivalent hydrogens are, how many hydrogens are adjacent to those four hydrogens? We have 1, 2, 3, 4. Let me circle them in green here. Green. Okay. We have all four of these hydrogens right here are adjacent to A. So that gives us a 4. 4 plus 1 is 5. So A is going to have 1, 2, 3, 4, 5. Okay. Oops. Now let's do B. Right here. B is going to be, let's see, there are 2 hydrogens and they are 1, 2, 3. So all 4 of these hydrogens are next to them. And these hydrogens, which are not even bonded to the same carbon, are not equivalent. So we have to count them. So we have 4, 5, and 6 hydrogens. And let's see, and 7 hydrogens. And this is to carbon. So we have 7 hydrogens. And let me circle them all in right here. 1, 2, 3, 4, 5. Oh, those are the ones we're doing. Not that one. 5, 6, 7. So that's 7 plus 1 is 8. Okay. One, 2, 3, 4, 5, 6, 7. There's only 7 because these 2 are the ones we're doing. So it's going to give us 8 peaks. Okay, so let's look at C. It looks like we're going to have the exact same splitting on C. So we're going to have 8. Let's look at D. We have, let's see, 1, 2, 3, 4. And let's see, 1, 2, 3. Oh, and then we have these 3 here. So that's 7. So that's going to be split into 8. 1, 2, 3, 4, 5, 6, 7, 8. And these hydrogens are only adjacent to this hydrogen by 3 bonds. So E is going to be a doublet. Okay. Now, why didn't I do it by position here? They're all going to be between 0.8 and 1.2. They're all hydrocarbons. They all have 2, 1, 2, or 3 hydrogen bonds. So there's no way to tell. So right here, you have to go by splitting, or you have to go by integration, or knowing that the number of peaks was correct. Okay, questions on that? This is the hardest one. I do not do this on exam. I only show you to demonstrate the spatial uniqueness of it. Okay, so let's go the other way. Let's look at a NMR and see if we can pick which compound it is. Okay, well, how do you know the N? The N is the number of hydrogens that are within 3 bonds of the hydrogens you're looking at. Okay. So the N is the 3 bonds. So it can be 2 or 3, because sometimes you can have them on the same atom, but they are that. So let's see here. We're going to blow this up just a little bit for a second here. Okay, so this is a quartet. There's 4 of them here. if this shows up on an exam, I'll tell you how many there are. That's triplet, and that's a singlet right there, okay? So we can go through our compounds and predict which of these is going to give this signal, or just 3 signals. Let's figure out which one's going to give us 3 signals, okay? So, okay, this one's going to give 1, 2, and 3 signals. It only has 3 carbons with hydrogens on them, none of them are equivalent. So this will give 3 signals. So that's a candidate. That would be 1, 2, 3. Okay, that's a candidate, 3 signals. 1, 2 signals. Why are there only 2 signals here? These are equivalent right here, and then these are equivalent because of symmetry. So this has 2 signals, so it can't be that one. Okay, and this has 1, 2, 3, 4 signals. So it can't be that one. All right, we're down to 2. Got a 50-50 shot. Okay, so let's look at our position here. We have something that is next to 3 hydrogens that is shifted way up. It's up to 4. So that has to be something that's directly bonded to an oxygen. Okay, so it has to have something that is directly bonded to an oxygen that's next to that. Remember, this pattern of 3-4 is an ethyl group, CH3, CH2, because this one right here will give it a triplet. This one right here will give it a quartet. So this ethyl group looks like this, but not only that, the CH2 has an oxygen on it because it's way up here at 4. So it has to be the first one.
That's not one of the oxygen.
This ethyl group is on the oxygen. So this CH2 is bonded directly to the oxygen. So it has to be this one. Because let's think about what the split pattern would be here. We would have the quartet here and the triplet here, but we would have a singlet over here. Okay. We'd have the quartet here, the triplet here, and a singlet here. Okay, but this right here would be closer to where this is bonded. It wouldn't be shifted that high. This would be, this right here, the one bonded directly to the oxygen, would be a singlet, and it would be up in 4. See, that's why you can tell the difference. It would be a singlet at 4, would be the second one. A triplet, a quartet at 4 is going to be the first one.
So the quartet in the first one is actually the last carbon.
It's actually, no, it's this one right here. It's the one bonded directly to the oxygen. The singlet is the one right here on the end.
Oh.
Okay. So you can see, you can piece a bunch of stuff together. You can eliminate choices just that don't even have the right number of signals, right? And then you look at shift and position and splitting to answer any other question. Okay, so now we want to think about question. Oh, there's a question there. Can you explain why the first one is better again? Okay, 2 reasons. All right, let's predict on just these 2 what our splits would be on here and where our shifts would be. So this one right here would be a singlet around 4 ppm. Okay, this one right here would be a quartet around 4 ppm. Okay, we have a quartet around 4 ppm. Therefore, it is the best choice. Does that make sense? Okay, excellent. I think that would clarify it for a lot of people. All right, so now we have to look at this and we can say, okay, we got a singlet, but wait a minute, that's something that's way high. That's like 6. So what does that have to be? You know, because oxygen only goes up to 4, bromine only goes up to 3.7. So that has to be a double bond. In fact, it has to be hydrogen on a double bond. And notice it's not split, it's a singlet This is a triplet. No, that's a quartet, sorry. Quartet, and that is a triplet, okay? All right, so we have 3 signals. So let's go through and eliminate things just by number of signals, okay? So let's see, for here we have hydrogens here, 1 signal, 2 signal, 3 signal, and then symmetry, okay, maybe. Let's see, 1 signal, 2 signals. Oh, there's only 2 signals on that one. We have 3 signals in our spectrum. Can't be that one. 1 signal, 2 signal, 3 signal. Okay, that might be it. 1 signal, 2 signal, 3 signal. Okay, that's okay too. All right, so now let's, yes. Yes. How can we eliminate something? We can eliminate this one because there's a double bond somewhere in the structure. So we can eliminate this one. So now we're down to 2. So now we have to look at where our other shifts would be, okay? So how far up would this be if it was just bonded to a carbonyl? Is it going to be as high as an oxygen or not as high as an oxygen? You want to say something bonded directly to an oxygen, it'd be right around 4. Something directly bonded to a carbonyl is going to be around 2.5 because it's a bond away from that. And we have a partially positive carbon. That takes the shift from having all the donation, carbon sucking up some of that electron, and it pulls it down. It would be down here at 2.5. Okay, so that means we have to have it be this one. We looked at our number of peaks first. We then looked where those peaks were. Okay, if you remember, have to remember some numbers, you know, around 6 is an alkene, around 7 is a benzene, around 4 is an OH. I'm sorry, a oxygen. So, okay, questions on that? I just wanted to run through this and have you use those rules to try to look at this. See, you can do this. Do the homework now. And again, it'll be due on next Wednesday when we have our next quiz. I don't know why it got shifted to Monday. They should have all been done on Wednesday because that's when our quizzes are. But anyway, so look for that and we'll continue there. All right, any questions on this?
Wait, the chapter 8 is due?
Chapter 8 will be due by midnight.
Oh,
Chapter 8 homework will be due by midnight. Okay. So let's go back to our NMRs here. Okay, and we had done our splitting and we had done our shifting. We were just about to talk about benzene. Okay. Okay. Do you feel that this activity helped you understand? Okay. Excellent. Okay. Good. Okay. So now we're going to talk about some other kind of special things. I said benzene start around 7, but they actually have some really cool splitting on them. So in the case of benzene by itself, and again, you have 2 whole chapters on it next semester, but I'm just going to introduce it here. If it doesn't have any substitutions on it at all, it is at 7.27. Okay, so it's above, you know, the alkenes are at 6, benzenes are at 7. Okay, so, but when you substitute the ring, weird things happen. Okay, so if we substitute the ring here, where we have a something that doesn't have electron donating or withdrawing, like just an ethyl group here. Okay, these hydrogens are equivalent, these hydrogens are equivalent, and this hydrogen is separate. Okay, but because there's no electron donating or electron withdrawing, it doesn't change them very much, and they look like a big clump. Okay. Benzene itself has a single signal when it's not substituted, but it has this clump of signals because these are splitting these, and these are splitting these, and these are splitting these, but the shift is not very high. There's not a lot of difference between them. Okay. What if you put an electron withdrawing group here? This is a carbonyl, so this is a partially positive side of our carbonyl, and it's going to draw electron density away. So it means that these hydrogens are closest to that electron, that oxygen, which means they shift downfield. So they are separated out. And then the one hydrogen is here and the two other hydrogens are there. Okay, so we do see some splitting. It's very small, but we see it. Now, what if you put an electron donating group in? So what happens with an electron donating group is these go upfield. So notice we're shifted above 7 now. We're below 7. I'm sorry, we're below 7. And these didn't shift at all. So those are the other 3 because they're too far away. Okay, so we see this really cool splitting pattern. Okay, so then that's just one thing that has everything to do with whether it's electron donating, it's shifted up to 8. It starts at 7.2, and with electron withdrawing, it shifts up to 8. With electron donating, it goes below 7. Okay, so there's another thing we can see. Oh, then so that's proton NMR. Okay. Now we're going to shift gears and talk about carbon NMR. So this activity, again, the benzene stuff is one of those things that might show up on an exam. So look at that slide a couple of times before an exam, and you'll do that. Okay, so next is going to be carbon NMR. Carbon NMR is different than proton NMR. Okay, one of the reasons it's different is hydrogen 1 makes up about 99% of the isotope you see. Okay, naturally occurring. Okay, so it's very, very common, and so there's a whole bunch of it in your system. That's why it splits itself. In carbon, we're looking at carbon 13. Carbon 13 only has a natural abundance of 1.1%. Okay, so that does a couple things for us. Number one, it eliminates spin-spin coupling. So we don't have to worry about splitting. We only get single peaks. Okay, we only get single peaks. And so all we have to worry about is shift. Also, because it's such a low abundance, we can't do intensity either. There are some modern techniques where you can get close, but it's not great. Okay, so in our carbon NMR, what we're going to see is on our x-axis here, we're not going from 0 to 10 anymore. We're going from 0 to 220. In this one, it's only 200. But we have things that go all the way up about 220. So it's a wider range. Okay, but the shift rules still apply. The more, if you're bonded closer to an oxygen, you're going to keep shifting over and over and over. And by the time you get to a carbonyl, they're above 200. Okay, so let's figure out the most important things about carbon 13 NMR. Okay, we don't have to worry about intensity. We don't have to worry about splitting anymore. So number of signals, okay, and position. Okay, the relative scale about where things shift is the same for carbon NMR as it is for proton NMR. Okay, so let's look at those ranges here. Okay, in this case here, the carbon shift is a little bit different with the halogens, but it's a really broad range right here. But when you have it bonded to nitrogen or oxygen, it's going to be between 80 and 40 for oxygen, or even down to 20 for nitrogen. Okay, so that's about the same kind of range we got for our, at least those positions were the same. Our acetylene carbon is shifted up a little bit from where it was in hydrogen. But notice this, our 3 hydrogens is lower than our 2 hydrogens is lower than our 1 hydrogen. That follows exactly with proton NMR. Okay. And then of course, when we go up to our next thing, we have this is cyanide. We didn't do that in proton NMR because we don't have a proton on it. The carbon and benzene will shift between 120 and 150. And alkenes will be in that same range, 120 to 150. But the alkenes can be a little bit lower, all the way down to 100. Or 110. Okay. And now we have the next group here. These are carbonyls. that have an electronegative element attached to the carbonyl. So that's your amides, your esters, and your carboxylic acids are all higher than benzene, 150 to 185. And then the only thing that's above 200 here are aldehydes and ketones. So if you see anything above 200, you're looking at that. If you see anything above 150, you're looking at a carbonyl with an electronegative atom on it. See how we're moving down just in the same general trend we saw before. You might want to get a few of these kind of memorized, but we'll see. So let's look at the actual values here. Again, the alkyl with 3 hydrogens on it, 0 to 40. 2 hydrogens on it, 10 to 50, and then 15 to 50 for the just 1 hydrogen on it, and 2 other carbons. Okay. The alkyl halides or the amines are both in the 10 to 65 range, and oxygens are 50 to 90. So see how these are still shipped a little bit higher than the halogens and the amines. Okay, the oxygen usually shifts it higher. Alkynes in a slightly different position, 60 to 90, so we'll shift it further downfield. The alkenes are 100 to 170. Benzenes are 100 to 170. So, but you can tell the difference in them by what kind of structure you have. The nitrile, it's very narrow range, just like in its IR thing. It's got the 120, 130. The carbonyls with electronegative groups are the 150 to 180, with the oxygens being higher because they are more electronegative than nitrogen. So nitrogen's just below it because of its electronegativity, oxygen's just above it. And then if you don't have an electronegative atom on here, you have just carbons or hydrogens here, boom, up to 215. Yes.
So if we talked about a proximity to something that's electronegative, it's going to shift it downfield. Why
Correct.
would
If you're the
aldehydes-
closer you are to it, the more downfield you're coming.
Okay, so why would aldehydes and ketones that don't have those electronegative atoms be perfect?
Because they are looking at, there is nothing donating to this partially positive charge. And our electronegative atom is the oxygen that's pulling all the electron density away from the carbon. So you have 2 bonds to oxygen. In the ethers, you have 1 bond to oxygen. In the carbonyls, you have 2 bonds to oxygen. Plus a bond of nitrogen or oxygen in the esters and amides. But we don't have anything to help balance out this positive charge. So the oxygen's getting it all, it shields it most, it's furthest down. Okay? Does that make sense? All right. So we also have to figure out the different signals we have. And again, this is where it comes into looking at symmetry and bond attachment. Okay. So in the case of this one right here, we did it by, in proton NMR, we said we had 2 different, well, they were the same though. They were the same. So we had 1 signal for hydrogen. Well, if they had the same signal in hydrogen, they're going to have the same signal in carbon. Okay. So this is only going to have 1 carbon signal. Now, when we have 2 carbons here, in this case, we're putting a chlorine here. So that means this carbon is going to be further downfield because it's bound to the chlorine, and it's different than this carbon. So we're going to have 2 signals. Okay. Now, this is the one that kind of throws people off. Okay. In this right here, how many hydrogen signals do we have? 3. Hydrogen? How many different kinds? We have hydrogen, hydrogen. So we're going to have 2 hydrogen signals. How many carbon signals do we have? 3. You got to count the carbonyl. Don't forget to count the carbonyl. The oxygen doesn't count, but the carbonyl does. So we're going to have 3 carbon signals. Okay. This is where people, because we didn't count carbonyls when we were doing hydrogen. So make sure when you're thinking about carbon, you're looking at that carbon, that carbonyl as a carbon. Okay, so let's look at the number of signals here. So this is a really typical thing. Notice how the baseline here is a little fuzzy. That's because, we only have 1.1% of these carbons were carbon 13. And so it's a little bit noisier. But we have one signal, two signals, three signals. It looks like this one's going to be the most hydrocarbon-like. This one's going to be next most hydrocarbon-like. And then this one's going to be bonded to an electronegative atom, right? And so this one's probably attached to that one because it shifted downfield partially. And this one's probably the farthest away from our material. So let's look what we have. We have propanol right here, one propanol. And so the one that's closest has to be that one here because it's the furthest downfield. It's the only one directly bonded to the electronegative atom. And then the next one here has to be attached to it because it's partially downfield because it's within two bonds of the oxygen, but it still has the carbon there. And the last one is this one right here because it's the furthest away from our electronegative atom. So we have three signals from three different carbons, and we have their shift positions identified by their proximity to the electronegative atom. Okay, questions on that? Believe it or not, that's all you need to know about carbon NMR. Shift and number of signals. But don't forget the carbonyl, write that down. Don't forget the carbonyl. Okay, so a little bit of, going through the homework and making sure that you got the, this section here right, and these are all in the high end right there. Kind of get them stacked in your mind so they're kind of right, and then we can do it. All right. So in our last 15 minutes, I am going to do mass spectrometry. Okay. On class on Monday, we're going to do a carbon-13 in-class activity and then a hydrogen and carbon-13 in-class activity. So if you're in class, you can do that live. If you can't, those are already uploaded to Canvas and you can download them at your leisure.
Are we going to turn those in?
No, this is just for you to get a handle on it because it's, and then the, I'll publish the keys if you want to double check yourself. Okay. Okay, so in the case of mass spectrometry actually tells us some cool stuff. And I'll tell you the 4 things to look for in mass spectrometry. Let me tell you how it works. In mass spectrometry, what we do is we take a molecule and volatilize it. And then we hit it with ionizing radiation and gives it a positive radical charge, okay? Now, when they have it as this positive radical, they can, number one, separate them by mass because the number of charges per unit mass. And then you can figure out, oh, well, this is higher, this fragment is higher mass than that fragment, okay? And so then they kind of actually can be separate, they decompose. And these are the fragments that are actually analyzed. If it's neutral or if it's just a radical, it doesn't matter. They're going to use magnets to pull the positively charged molecules into the system and separate them out, okay? So the way we usually do this is with an electron beam. And so what that'll do is that'll break any of our carbon-hydrogen bonds to give us a radical cation somewhere and an electron. So we've actually not changed the oxidation state of there. We've just knocked one of the electrons off, giving it a positive charge. And usually it knocks off one of the hydrogens when it does that. Okay. So, and when it does that, it does a whole bunch of stuff. But okay, so let's take roll. Hang out to the last 15 minutes of class, take roll today. Nobody left. Good. Everybody got so when we look at a mass spectrum, we want to think about it as a fingerprint, because what we're going to see is we're going to see a bunch of different things. And when we look at these different things, you can actually take that same compound, run it at another mass spectrometer, and it's going to decompose in the exact same way. It's going to fragment in the exact same way. So that when we have that, you can actually use it as an analytical tool that I have this compound in my library, I can say, oh, look, the stuff I scraped off the assailant shoe is canola oil because it fragments exactly like canola oil. So that's how, the guys who do, NCIS or CSI, they actually have libraries of compounds. And so when they say, oh, this was lactic acid, it's like, well, yeah, because it matched the mass spec. And so this is one of those devices they use for that. Okay. So the four most important things we need to look at is the molecular ion peak. The molecular ion peak, write this down, is the highest molecular weight peak on our spectrum. Okay, it tells us the molecular weight of what we're trying to analyze or our analyte. Okay, so it's not always big. Sometimes it's very small, but it's going to be the highest molecular weight. Okay, the next thing to look for is what we call the base peak. Okay, the base peak is the tallest peak. Okay, it means that it is the most stable fragment or most likely fragment to be made. And we balance that to be 100%. And that's why we call it the base peak. Okay. The next thing we want to look at is relative abundance. So the different fragments you have are going to be there. Sometimes you'll have a very large parent ion peak or molecular ion peak. And that's because the molecule is very stable. Okay. But the base peak is always going to be the largest peak. Okay? But then you're going to have other fragments. So if you have a long chain hydrocarbon, like hexane, you're going to see it break off a methyl group, a CH2, a CH2, a CH2, a CH2. So you're going to have a specific pattern in it. And then we look at fragmentation pattern. Okay. And so we're going to see that, oh, an ethyl group fell off or a T-butyl group fell off. You can see you can start to build the structure by looking at that. So let's look at the fragmentation pattern of pentane. So pentane's a large hydrocarbon. It's a straight chain hydrocarbon, which means that if it breaks apart and forms a cation, or radicals there, they're all going to be about the same stability. So what we see here is our molecular ion peak is this highest peak here. Okay. Now notice there's this little tiny peak right here. This little tiny peak right here. It's 1.1% of this peak here. What is it? Carbon 13. That's why we always do a mass spec right after carbon 13. Okay, so that's carbon 13. So you're always going to get this little peak, but that peak doesn't count because that's the isotope, which means this is our molecular ion peak. It's the highest molecular weight here. Now look what we have here. We have it. Our next fragment here is 15 mass units below our molecular ion peak. Carbon's 12, hydrogen's 1. So a methyl group is 15. So it lost a methyl group. And guess what? This one right here is 14. It lost a CH2, or it lost an ethyl group. An entire CH2, CH3 is 29. So that means this most stable peak is where it loses a methyl group. An ethyl group. Well, it can lose an ethyl group from that side, or it can lose the ethyl group from this side. So it makes sense that it'd be the highest ion, right? Because you can break it from either side and get to the same peak. Then we have our 29 and 27 peak, which is our ethyl group here, and then with a couple hydrogens lost. And then we have our methyl group, or CH3 here. So our fragmentation pattern is basically a carbon and hydrogens, carbon and hydrogens, carbon and hydrogens, carbon and hydrogens, until it gets down to that. Okay, see how that fragmentation pattern fits the structure of the molecule. Okay. So let's look at what those fragments look like. So starting from one side or the other, you can just start going, okay, break that off. That's going to give us this peak and that peak. Okay, but then it's also can fragment such that it gives us this methyl fragment. And notice we don't see this one. We don't see that one because it doesn't have a positive charge. We only see things with positive charges. So this radical we don't see. This radical we don't see, but we do see the charged version of it. So when it breaks apart, one's the radical, one's the positive charge. Okay. So then in this case here, we have it breaking instead there, we have it breaking here. And so that gives us these fragments here. And these fragments are, again, we don't see that one and we don't see that one, but we do see the positively charged one and the positively charged one. Okay. See how it equates to the fragment and the molecular weight of those fragments coming off. And we see them as positive charges. Okay. So another reason we have that other peak at 41 and 43, let me go back to the spectrum here. See, we had 43, but we also have this peak here at 41 right here. So we have a lot of little peaks in that big fragment. And the reason we have that is that it's more stable for this compound because it's a primary carbocation. Remember, we don't form those in solution. We only form those in gas phase. And it wants to be a more stable carbocation. So it loses a hydrogen from this side and becomes an allylic carbocation. Remember, allylic carbocations are more stable than tertiary carbocations. So it made itself more stable just by losing a hydrogen, or two in this case. So that's why it's 2 mass units below that. Okay. All right, questions? Okay. And all right, 5 minutes to do 5 slides. Okay. Oh, we're not doing that. Okay. Oh, yeah. Okay, yes, we're doing this, but we're gonna pick up on determining the molecular formula on Monday. Plus, we're also gonna do in-class carbon and proton and carbon NMR. Okay, I'll pick up on this on Monday. All right, any questions at home there? Okay, okay. Good. Yes.
I don't have those slides I downloaded.
Oh, you don't?
No, I have this principal stabilized to the last slide I have, and then I have. I don't have the last. Did you download the student version or the last slide? That's the last thing
Okay, great. That's what I wanted. That's actually, I thought I checked it. Yeah, those are the last. Yeah, that's why I wanted to wait, because I thought I took them out.
Yeah.
So, all right, yeah, I actually took a couple of those out, some of those slides out. We'll talk about that on Monday.